presenter, Stephen Chmely. Dr. Chmely is Assistant Professor of Agricultural and Biological Engineering at Penn State. His research interests include emerging bioproducts, additive manufacturing, synthetic chemistry and lignin, and catalytic transformations of biomass. He's a member of the Mass Bio project team devoted to bioproduct conversion processes. So Dr. Chmely, welcome. We look forward to your presentation in today's seminar. Escape and bring up your slides.
All right, wonderful. So thanks everybody for having me. As Dr. Chilton said, oh yes, my remote's going to work today. That's good. So today I'm going to talk to you a little bit about the research that we do in my lab here at Penn State in the Department of Agricultural and Biological Engineering. And I'm going to talk to you a little bit about biorefining and how that could be America's newest frontier. So some things to talk about. We're going to first talk about what refining is and sort of answer the question, can we refine biomass? Then we're going to talk about lignin valorization using catalysis, so trying to add value to lignin. And we do that with transfer hydrogenation and hydrogenolysis. Maybe I should point with this one instead so people online can see. And then we're going to talk about incorporating lignin into new soft materials. And we do that by 3D printing by a process called stereolithography, and how we can make new photopolymers with lignin. So we'll talk about all those things today. So in terms of refining, you probably know that petrochemical refining is a suite of industrial technologies that turns oil into useful products. What you may not have known is that when you look at a barrel of oil like this one, and everybody who's seen the DOE white papers on petrochemical refining has probably seen a figure that looks like this one. But the high volume product that comes from a barrel of oil, in fact, 76% of the volume goes to energy extraction. That is production of gasoline, diesel, jet fuel. And those things are combusted. They form CO2 and water and energy. And a very small, by comparison, volume fraction, about 17% of the barrel, goes to the production of chemicals. And in fact, these six that I have here, this is ethylene, propylene, butylene, benzene, toluene, and xylene. Those six go on in other industrial processes to make something like 10 or 20,000 other chemicals. And so, whereas there's a huge disparity in the two volumes, there's much more fuel that we make from a barrel of oil than other products. In fact, the economic value is approximately the same. From this very small fraction of carbon, we get a lot of money. And so we like to say that it's the products that keep the lights on at the refinery. And so we want to think of biorefining in the same way, that we can extract energy from biomass by turning it into, for example, liquid fuels like liquid jet fuel, but also make some high value products. And that's the focus of the research in my lab, is the production of those high value products. All right, so you've probably seen a slide that looks like this one before. The carbon cycle explains how carbon is exchanged among the ecospheres on Earth, right? So a tree dies and decomposes and turns into petroleum, which we then dig out of the ground and put in a barrel. And then we use that barrel of petroleum to make products like fuels for jets and cars or things that people need. Those eventually are used up, they're burned, or they decompose, they form CO2, which then is taken up by the next tree, and so on and so forth. So the problem, or I should ask you, what is the problem with this picture as the way I have it drawn? Any thoughts?
The time component.
Yeah, exactly right. I didn't tell you anything about the time component, right? But it turns out that the process, this first step in the process takes 300 million years. So none of us will be alive. None of your children's children's children will be alive when trees that are alive today turn into petroleum. The petroleum we're digging out of the ground, came from trees, from plants that died 300 million years ago. All right, and so what happens is, as we use this petroleum, CO2 builds up in the atmosphere because the plants can't decompose to form new petroleum fast enough. So we get this buildup of CO2, which we believe contributes to anthropogenic climate change. And so the question is there a way to short circuit this process? So instead of turning plants into petroleum that we then use, could we turn plants directly into a useful product that either is or looks like petroleum, and then use that to make the products that we depend on, like fuels and other chemicals and plastics and things like this. So this is the type of work that we do in my lab, trying to short circuit this process to make those useful products. So lignocellulosic biomass is our focus in the lab. And lignocellulosic biomass is plant terrestrial biomass that's composed of cellulose, hemicellulose, and lignin. In other words, we like to think about the non-food components of biomass. Whereas ethanol is produced in the United States anyway, primarily from corn, we don't want to use food to make things like ethanol or other products. So we focus on the structural components of biomass. That's the cellulose, hemicellulose, and lignin. And these are the parts, the polymers in the plant that allow the plant to stand up straight, conduct water, grow towards sunlight. And they're similar to the components in concrete, right? So concrete is a composite material. It's composed of cement and rebar or other aggregate. And it's all sort of glued together. And this is how the plant builds its composite material to give itself structure. So the lignin is kind of like the cement, and the cellulose is kind of like the rebar. And the hemicellulose is sort of an additive that helps everything come together. So we're interested primarily in lignin for two reasons. Number one, and there's a little bit of chemistry I should mention. My background is chemistry, so there's a little bit of chemistry in these slides, but don't panic. Won't be a whole lot. We'll talk a little bit about how the chemistry works. But lignin has a lot of these, what we call hydroxyl groups. And these are sites where we can do chemical reactions and change lignin to allow us to do things with it, to incorporate it into new products. And not only that, but they have these, what we call aromatic rings. And so these are areas of delocalized pi electron density that have high absorption cross-section. What that means is they absorb photons, especially UV photons. And this will become important when we talk about 3D printing by stereolithography, because this is a photopolymerization process that requires UV light. And lignin is very good at absorbing UV light. So we think that lignin will work very well for the processes that we want to do to make new products. All right, so I told you we're going to talk about biorefining, and we'll come back to lignin, but this is a suite of industrial technologies that turns biomass into useful things. Just like petrochemical refining is a suite of technologies that turns crude oil into a target bag, biorefining is an industrial technology that turns biomass into useful things. And so this is just one of many types of schemes that could be useful for biorefining. But you could imagine if you took, this is a block flow diagram, if you took biomass and you did some sort of conditioning step where you remove things like extractives or ash in organic materials, you're left with now a feedstock that we could fractionate. And fractionation is just a process where it separates all of the things that make up biomass. So it separates the lignin from the cellulose and the hemicellulose. So in this case, we could take the cellulose and the hemicellulose, those are the polysaccharides, and for example, use microbial conversion, feed those to microbes that convert sugars into fuels. And then we could take the lignin and do some sort of chemical conversion process and turn that lignin into advanced materials. So as I said, this is just one of several ways to do biorefining, but I think it's useful to think about it in this way, because if you think back to the barrel of oil, where you have 3/4 of that barrel is used to make fuels and 1/4 is used to make products. If you overlay the analysis of biomass on top, you see that, and it depends on the species, but biomass is approximately 60% polysaccharides and 25% lignin. So if you could turn all the polysaccharides into fuels and all of the lignin into materials, then you have a process that looks similar to what we already do with petrochemical refining, where we turn the majority of the carbon in petroleum into fuels and a small fraction or relatively smaller fraction into products, but still make quite a lot of money because this fraction is very valuable. And again, the revenue, as I mentioned, is nearly the same. All right, so if you've ever worked with lignin or you know anybody that's worked with lignin, you've heard this saying before, that you can make anything from lignin except money. It's for 50 years, people have been saying this, unfortunately for people like me, because then you go to a funding agency and you say, I want to do something with lignin, and they laugh at you. That's not exactly the case, but it remains to be seen what exactly we could make that's useful from lignin that will actually make any money. The issue is that, 10 years ago, when you look at ethanol biorefineries, if you have, and this is a slide from my colleague Joe Bozell, who says, look, you have 100 gallon of ethanol per ton of biomass facility. So you just do some back of the envelope math. You have 18% of that is lignin, which is in corn stover, and you have a 30 million gallon facility will produce about 54,000 tons of lignin per year. And the question is, well, what do we do with all this lignin? We're producing ethanol from the polysaccharides, and we've got all this lignin with nothing to use, nothing for it to be useful for. And all of these industries say, well, we're just going to burn it. And that's certainly a useful product, especially when you talk about ethanol refining, because you can use the lignin to generate what we call combined heat and power, right? So the plant doesn't have to buy electricity. It generates its own electricity by burning the lignin. But the question is this really an effective use for lignin? Could we generate additional value from lignin by doing something other than just burning it for fuel? And we think so. And a lot of people think so. So I told you my background is chemistry, and I like to think about biorefining from the chemistry standpoint. And we know that for petrochemical refining, 85% of those processes require catalysis. And so we don't think biorefining will be any different. Remember, a catalyst is a chemical compound that speeds up a reaction. And it's not changed during the reaction, and it's reusable. So it allows reactions to take place quickly. And we think we can apply catalysis to biorefining in the same way that it's applied to petrochemical refining. So here we have a cartoon of lignin. Remember from a few slides ago, I showed you lignin. So here we have some sort of lignin. And the question is, could we do some sort of hypothetical deoxygenative process? Could we essentially magically delete all of the oxygens? And if we do, if we just delete all the oxygens, we get compounds that look like these: benzene, toluene, ethylbenzene, xylene. Remember, I showed you on that slide with the barrel of oil that those were 3 of the 6 chemicals that are used to make just about everything else. So if we could turn lignin into these compounds, then we essentially have won, right? Because petrochemical refining already knows what to do with these. So we just take this and turn them into these, and then sell this to a petroleum refinery, and they make all the products that they currently make from petroleum, except they're making them from biomass. The problem is that this process is very difficult to go from here to here is very challenging. So I'll mention again, BTX, critically important. I told you already, it's used to make lots of things. You look down this list, paraxylene is used to make terephthalic acid, which is one of the monomer components of polyethylene terephthalate, which is the plastic that's in every water bottle that you buy in a grocery store. Right? PET is a polyester that's used in water bottles, and et cetera. And it's actually the most recycled polymer of all of them. So just this one by itself, if you just ignore all the other ones, but look at some of the other things: pharmaceutical intermediates, chemical intermediates, solvents, gasoline, coatings, food enclosures, resins, paints, food packaging. I mean, you name it, it came from BTX. And so, but as I said, it's very challenging to go from lignin to BTX to make some of these useful materials. Now, it would be really great if we could do that, because if you think about refining from platform chemicals to advanced products, here we have this graph. We have on the vertical axis, think about molecular complexity. So how complicated is the molecule? And on the right hand, or on the horizontal axis, you have process coordinates. So you're doing a transformation. And as you do chemistry, your molecule goes from something very simple to something very complex. So you start with what we call a platform chemical. You do some refining process and you get some product out. You start with xylene and you do some petrochemical refining and you get a plastic water bottle, right? So you go from something simple to something complex in petrochemical refining. In biorefining, we start with something that's pretty complex, right? A tree, chemically speaking, is very complex. It has lots of complex polymers in it. And the question is, well, how do you get to advanced products from biomass? And there's essentially 2 ways to do this. You could do what I would call traditional biorefining, which is what I showed you, where you turn lignin into BTX by doing some process here, and then we already know the blue line. So as long as we could get to a known platform chemical, we can just build it back up into an advanced product. right? But what you're doing in this case is sort of robbing nature of the complexity of biomass. The tree spent a lot of time and literal energy putting those polymers together, only for us to come and undo all of that work to make these simple products, then that we have to build back up into advanced things. And so the question is there a way for us to go from this really complicated thing to these new advanced products along this hypothetical dotted line, which is where the research in my lab is focused, on these new ways to make advanced products from biomass. And so the one that I'm going to show you that we focus a lot on is this catalytic deconstruction. So I showed you this, got this hypothetical deoxygenative process, and you make these things. This would be the traditional biorefining, where you take something complex and turn it into a simple, relatively simple suite of molecules that we already know how to build up into new things. But what we would rather do is a selective process that gives us molecules that are a little more complex, that maybe we don't know exactly what to do with yet, but will make what we call bioprivileged materials. And those are materials that we either cannot make from petroleum or are so complicated or difficult or expensive to make from petroleum that we don't bother, right? So instead of making polyethylene terephthalate, we make something that you could only make from biomass. And we get the advantage that it only comes from biomass, and it's much cheaper that it comes from biomass. And oh, by the way, it's potentially renewable and sustainable because it comes from biomass. So we have to change then the process that we use to create these, what we call bioprivileged materials. And this is the first part that we'll focus on, the selective catalytic process. So I told you there's a little bit of chemistry, and I just wanted to show you why we're interested in particular in this process for lignin. So we talk about the redox or the oxidation state, or how much oxygen is at this alpha carbon, which is important for the properties of new soft materials. Right? So this molecule is called guaiacol, and it comes from lignin. And you can imagine if you add a molecule here, we'll just call it L, something here that's polymerizable, we can make a new polymer by linking a bunch of L's together. So now imagine you have a chain of L's, and at each L, there's a little thing hanging off, the spinach, I like to call it. It's a little thing hanging off this chain, and it looks like guaiacol in this case. Or it might look like other things depending on how this aromatic ring is substituted. Right? So the properties of your polymer, which is this long chain of L's, depend on what this ring looks like. If we change our ring a little bit, we have a complex that looks like this. Here now we have an R group. So this R is a variable. It could be, for example, an H or a C double bond O. You do the same thing and you get a new polymer. Looks exactly the same, has properties that depend on not only what's attached to the ring, but now we've got this R group. So depending on what the identity of this R group is. And finally, if you have a molecule that looks like this one, got a hydroxyl group, do a little bit of extra chemistry, you can put an L now at both of these positions. Remember, I told you that we're interested in lignin because it has these hydroxyl groups. And that's where we can do chemistry. And so we can put these L's here and we make a polymer that looks like this one, which is what we call cross-linked. And you may have heard of cross-linked polymers. If you've ever used like super glue, it starts out as a liquid and then it hardens. That process is called cross-linking. So you start out with a liquid material that eventually hardens into a new material because it cross-links. And this is exactly how we do 3D printing by stereolithography. So we could potentially tune the properties of our polymers based on all of these functional groups, right? Which is not something we do with petroleum because it's very complicated to go from, say, a benzene and add all this stuff on. But if we start with something that already has all the stuff added and we just do some chemistry, we could potentially make these really neat new materials. All right, so we talked about refining and turning biomass into useful things. Now we're going to talk about changing the lignin around so that it has just the right properties to make polymers, and then the polymers is what we're going to talk about at the very end. All right, so how do we change lignin? How do we valorize or add value to lignin so that we could make useful products? And we're going to talk about transfer hydrogenation and hydrogenolysis and controlling lignin chemistry. All right, so the primary focus of lignin valorization or adding value to lignin so far has been looking at these types of groups. Remember, I told you we want to hypothetically delete all the oxygens. So if you could delete these oxygens and you're left with this carbon here, maybe you have something that looks like toluene, which is this product. There's been a lot of work on doing that. The problem is when you do this type of reaction, it's not easily controlled. And without getting into the specifics, you can't really just magically delete the oxygens. You end up with product mixture that has still products that have oxygens, also some that have lost their aromatic character, some are oxidized, some are more reduced. So you think, oh, I'm just going to delete the oxygens, and what do you get as a mixture? And in chemical processing, mixtures are bad because you have to put another step in there to separate all the components of the mixture. So it becomes very expensive. So instead, what we're focused on is looking at the other side of this ring. We just ignore this part, and we want to look here. Because remember, I told you about the cross-linking. You got to have this thing has to be a hydroxyl group in order to do that cross-linking reaction. And so we want to see, can we do some chemistry to change this part into a hydroxyl group or deoxygenate it entirely? And is there some catalyst that will allow us to do that? And so the one process to do this is a catalytic hydrogen transfer reaction, where we use ethanol as a reducing agent. So you got to think back to general chemistry. What's a reducing agent? Right? Reducing agent is something that reduces something else and itself becomes oxidized. Maybe you've heard oil rig or Leo says GER or something like this. Redox reactions. That's what we're talking about. In this case, we have a compound that looks like this that has what could be a hydroxyl group at this position, but instead we're going to use ethanol and a catalyst to transform it from this what we call carbonyl group to a hydroxyl group, because this is the one that's going to allow us to do that cross-linking reaction. And what's nice about this reaction is that whereas you could do this with hydrogen gas, so see this H2 here, these two red hydrogens that end up on our molecule, hydrogen gas comes from methane, shale gas, which is a non-renewable resource, whereas ethanol comes from biomass. So if we could do this same reaction that we do industrially with shale gas, instead with a biomass product, then this could potentially be a more sustainable process. So we're interested in investigating the type of catalyst that we need to do this process with ethanol. And I'll just show you additional reactions. So you could trace where these hydrogens come from and where they go on the molecule, and you can get things that look like this one, or like this one, or an additional one that looks like styrene, based on the catalyst that you choose. And so I won't say too much about the actual catalyst production, but here we make these nanoalloys, which are catalyst materials that contain different types of metals. We're interested in first row transition metals. Those are things like nickel, cobalt, iron, because they have a high abundance in the Earth's crust. And so here we have a transmission electron micrograph, a TEM picture of one of the catalyst nanoparticles. You can see there's a scale bar here. This is 200 nanometers. So we look at the catalyst, and the colors are indicative of where the different elements are. And I think green was probably iron, and blue was nickel, and red was oxygen. I don't remember what the colors were, but the take home message is that you don't see any areas where the colors are concentrated, right? The colors are spread out among the material, meaning that the elements are all evenly spaced in the material. So when we do this reaction, I have a graduate student who's screening all of these materials. And what he does is he just takes this model compound and he tries to do catalysis, and he tries to figure out, well, what's going on with our species here. So we look at the conversion, or we do a reaction. Here are the conditions down here. So we take 50 milligrams of our catalyst, 10 volume% of acetophenone, which is this compound. And we do this at 300 C for 2 hours, and then we quench it in ambient temperature. So what we're looking at is how much of this turns into something else. That's conversion, right? So when we do with no catalysts, about 10% of this goes away and turns into other things. And in fact, it turns primarily into this thing. But when we add our catalysts, we'll see that here's our alloy catalyst, for example. 97% of this now turns into something else. And it turns into a mixture of these two things. 1-phenylethanol, which is the one that we want with the hydroxyl group, and ethylbenzene, which is one where the oxygen totally goes away. So we're trying to use these model compounds because it's more easy to track what's happening than if we just started with lignin, to try to see if we could get any information from these reactions. And we do, the chemist in me says, oh, let's look at some kinetics of these reactions, trying to figure out reaction rates, how fast the reactions occur. And so we can see some information about the kinetics and how the reaction actually takes place, and potentially some mechanistic information. So what's going on the surface of our catalyst. Once you do the reaction, you could take another TEM image of your catalyst and try to see, did the catalyst change at all? Because remember, a catalyst is something that speeds up a reaction, but it doesn't change, so you can use it again. And in this case, whereas before we saw an even mixture of all of the elements in our catalyst before the reaction, after the reaction, the elements have segregated. So now red is iron and green is nickel. They're no longer on top of one another. They're no longer mixed together. They're segregated. So our catalyst identity has changed, which means it wouldn't be something useful for us to reuse in another process. And we did some characterization of our catalysts. This is by X-ray diffraction. And essentially what we're showing here is that there aren't any features in this diffractogram of our catalyst material, meaning that our materials are amorphous. They're not little crystalline materials that are easy to track. But after you do a reaction, you start to see peaks, which again leads us to believe that our catalyst is changing. So this is bad news for catalysts, right? You want to be able to reuse it. If it changes, then you can't reuse it because you're using something different than the first time you tried the reaction. So instead, we moved on to this sort of second generation of materials, which are metal oxide nanoalloys, which we produce by this urea oxidation reaction, which essentially oxidizes the metal chlorides into metal oxides. And we get materials that look like this one. Move this over here. Here we go. Oops. That's not going to go away. It's really hard to mouse upside down. It's very challenging. Here we have another TEM image. So here's our nanoparticle. And this one's one of cobalt. You can see that there's cobalt metal on the inside, and on the surface, there's cobalt oxide. So it's got this oxide layer on the outside. And these are just more images of that phenomenon. Again, you can see cobalt here and this oxygen layer on the outside. So we go back and we do the same screening reactions where we start with our acetophenone and we try to see what type of reaction is catalyzed by these catalysts. And there's a lot of info on this slide, but what I wanted to point out was that we have some selectivity. If we're trying to make a product that looks like the blue thing, then we know, oh, we can use this iron catalyst. And if we want to make the green thing, we use this iron nickel boride catalyst. And if we make the orange thing, we use this iron nickel iron oxide catalyst. So it gives us some knobs to turn, if you will, to give us some selectivity that we can actually make the products that we want to make based on the catalyst identity. All right, so we were talking about biorefining, and I just showed you a bunch of model compounds because lignin is a very complex molecule, difficult to track what's going on. So we started with model compounds to try to get some idea of what's going on with our catalyst species. But ultimately, we're interested in this chemical conversion process to turn lignin into advanced materials. And so here's where we're sitting with this catalyst work. I want to turn this lignin into advanced materials. So one way to track changes in lignin is by doing what's called size exclusion chromatography, which just gives us a molecular weight distribution. So here we have on this horizontal axis, this is apparent molecular weight of lignin, and this is a log scale. So here we have 100, 1,000, 10,000, 100,000, et cetera. And so when you inject lignin into this instrument, you see that in fact, it's a heteropolymer whose structure is unknown and whose molecular weight is distributed. So there's some small number of molecules that have a molecular weight of about 100. And there's some small number of molecules that have a molecular weight of nearly 1,000,000. And most of the molecules have a molecular weight of, say, 3,000, something like this. And here we have maybe 1,000. So this response tells us how many, and this one tells us how much does it weigh, right? So you could think of it like a histogram. Most of them weigh something like 3,000 grams per mole. But when we do catalysis, we see that the molecular weight changes. What comes out is material that has a lower molecular weight. Now, most of them have a molecular weight of even less than 1,000, maybe 800. Some here, this is probably 200. So the molecular weight goes down. And when we add different catalysts, we see different distributions. Right? So our catalyst is changing the molecular weight of the lignin, but it also changes, remember, we're interested in that oxidation state. And so we look at we do some modeling of NMR spectra. So the NMR spectrum will tell us, in addition to a lot of structural features, also something about the oxidation state at this A carbon. So this is the one where we could either have this hydroxyl group, or we could have this C double bond O, or we could have nothing here. So we're trying to monitor what's happening at this A carbon. And what we see is that in the case of, here we have lignin that has not been catalytically treated. Here has been treated with just the solvent. Here's with our catalyst. So lignin starts out with things that look primarily like this red circle. This big blob here is this red, which is this one, which is why we picked our acetophenone monocompound. But after we do catalysis, most of the stuff that looks like the red circle goes away. And what you're left with is what looks like this green triangle, which is this compound, the one that where none of the oxygen is there anymore. But remember, the one that we want is this one that's got this hydroxyl group, the little blue square, which you see a little bit here. And the same can be said. We see a little bit in this area. These are for different types of lignin. So this one, you see some of this hydroxyl group, so that's good. And then this S type, it's a little more, I'm sorry, the G type is a little more challenging to figure out what's going on. But ideally, what we can do is monitor with NMR what's happening. Are we actually making this product that we want to be able to make so that we can do chemistry to actual lignin and turn it into useful polymers? And then we can look at the product slate by GCMS. So now we're actually identifying individual compounds that come out in our reaction. And what we see is an increase in things that look like, say, 8 or 12 or 19, where these green arrows are. Those things increase because there's no hydroxyl group at that alpha carbon. That's that one right there. And a decrease in things that look like, for example, number 9 and number 15, where we have, this is an aldehyde. Here we have a ketone at the beta carbon. So things where oxygen with oxygen in them go down and things without oxygen go up. But again, we'd like to get that intermediate one where we have that hydroxyl group in this case. We're sort of over reducing our material. All right, so we think we can prepare the material in such a way to make useful compounds. So now the question is, can we take the lignin that we prepare in this way and incorporate it into new soft materials where we can do photopolymerization and stereolithography? All right, so how does photopolymerization work? Imagine you have a vat of molecules. You have green molecules and blue molecules. And the green ones are what we call our monomer species. And the blue ones we call photoinitiators. And it's the blue one's job to absorb light, right? So you shine light, and the blue ones will absorb the light that you shine on them, and they become activated somehow. We won't really discuss how. There's several ways, but just know that somehow they become activated, and that activated state allows them to polymerize the green ones. So all the green ones hook to the blue ones, and they line up and they hook together, and you make these chains, these polymer chains. And this is what's happening when you mix your super glue. It starts as a liquid. In this case, in super glue's case, you don't need light to do this. You actually mix two chemicals together and they react and they harden. They form polymers like this. But in our case, the process requires light. Sometimes the process requires heat. It depends on the polymer system that you're using. But for us, what we use are ones that require light. So we call this a photopolymerization because it requires the light. And actually, the photopolymerization is useful for 3D printing in a process called stereolithography, which is actually the first 3D printing process that was invented, I think, in the 80s. I'm not exactly sure. But in stereolithography, this is an animated GIF from Formlabs, who's a manufacturer of 3D printers. You have a liquid resin bath here, and you can see there's a laser. This has been sped up, but you see the little laser is flashing back and forth here at the bottom. And when it does that, the liquid hardens in little spaces, and this platform rises up out of that liquid, and you have a solid object stuck to it. And this is a useful process for 3D printing for several reasons. Number one, this is a vat polymerization strategy where you have essentially a bucket that's filled with this liquid material that is, we say, underwater, which gives us this constrained surface configuration, meaning that the polymerization happens under the surface of the liquid. So you remove oxygen from the equation, which is typically bad for oxygen being around is bad for photopolymers or polymers in general. So we take the oxygen away, make these really nice materials. that have, this process has what we call high dimensional accuracy, meaning that the surface of the thing that you print is really high resolution. Think of an old, like an 8-bit video game sprite, right? It's very jagged edges because it's made with squares. And if you make the squares smaller and smaller, your resolution goes up because you can make now circles as opposed to squares. Same thing here. So with this laser, you can make really small, instead of squares, you're making cubes because it's 3-dimensional. But you get high dimensional accuracy, really high surface resolution. So it's useful in things where you need really high precision, like in medical implants or dental implants. Anywhere where you need a really smooth surface, very useful 3D printing process. So one of the things that we were interested in with 3D printing by SLA was monitoring both the what we call the critical cure dosage and the penetration depth. So the photons, imagine you have this liquid and you shine a light on it. The photons will travel some distance into the liquid, and then they'll meet one of those molecules that absorbs them, and then polymerization takes place. So the distance that it has to travel before it finds one of those molecules is called the penetration depth. And then the dosage, that's the number of photons you shine. So imagine a bright light has many photons coming out, and a dim light has few photons. That's the difference in brightness, right? Is the number of photons. So here the dosage is the number of photons, and the penetration depth is how far they travel inside the liquid. And these are very important parameters for 3D printing because if for example, if your material is opaque and none of the photons can penetrate, then the polymerization doesn't take place and your print fails because it doesn't harden. And this is important, especially for lignin, because if you've ever seen lignin, you know that it's brown. And so you might think, well, now you're making a material that's relatively opaque. And so if you shine light on it, it's going to be difficult to polymerize. So when we first started doing these photopolymerization reactions, we said, well, let's just take our lignin that we upgraded and dump it in and see what happens. And what you get are these heterogeneous samples. You can see that you have these resins with these little chunks. See the little chunks in there? That's lignin that doesn't dissolve. That's bad. We don't want the chunks, because when you try to print with the chunky stuff, you get these specimens that are sort of almost looks like they're melting off the build platform. So this is the build platform. Imagine the resin tank is down here and the object comes up this way and they look kind of gooey and not so good. And this is because you have this heterogeneous resin. You want a nice, smooth, homogeneous material if you want to get homogeneous objects printed. And so we can make homogeneous resins like this if we do some chemistry. And when we do that, we get nice specimens that look like this one. This is actually what we call a tensile testing dog bone. It allows us to test the mechanical properties of the resins that we make. And this is a window pane test. This is how we test that for that critical cure energy and that penetration depth. So once we homogenize our resins with some chemistry, we get these nice things that we can print, these nice objects, and they are brown. And so there's lots of engineering that we have to do to incorporate lignin into resins. Primarily, we have to do that reaction. Remember, I told you there's these hydroxyl groups. We got to do chemistry there to put this. I showed you before. It was this what we call an L group, a linker group. It's for the polymer forms. That's this thing here. So this is what we call a methacrylate group. We can add these methacrylate groups by doing some chemical reactions. So we replace the hydroxyl H with this methacrylate, and then we can polymerize. That's what gives us this nice homogeneous mixture. And resins, typically commercial resins, are mixtures of lots of different things. You have diluents. Here's the photo initiator. This is the thing that absorbs the light. Here's a molecule that has a UV protectant, a UV blocker. Here's the actual material that gets polymerized. So we started with this clear prototyping resin and added lignin to it. And what we can see, here's a plot of thickness versus the natural log of the dose. So how much light you add gives you how thick the material polymerizes, so how far the photons penetrate into the resin. And as you add lignin, what you see is that, so flatter is better. So even a large change in the amount of light gives you a small change in the thickness, which equates to really high resolution. Right, so you can make very small changes by adding more light, which is which is good for resolution. And was sort of surprising was that our resolution actually got better as we added lignin. We would have thought it'd be the other way around. As you add more lignin, resin becomes darker, it becomes harder to print with. It seems like it actually becomes easier to print with as we add more lignin, which is great news. It almost never works that way, right? Like you say, oh, well, you use lignin because it's sustainable, but the stuff works not as good. But in this case, we added more lignin and it actually worked better. So that was really great news. And then we can also test mechanical properties like viscosity of the resin, which I'll just mention. The viscosity is still low enough to work as a 3D printing resin. You can also measure modulus, which is a measure of the stiffness. You can measure elongation, which is the measure of how ductile the material is. And all of these properties improve as you add more lignin. And then I told you the surface resolution is really important. And so here you have electron micrographs of the surface. Here's the commercial resin. And as you add more lignin, you see that the surface is actually smoother. You get better resolution. You get better surface properties when you add lignin. And then I know I'm running short on time here, I think, but the photoactivity of lignin we can change by doing some reduction reactions. Allows us to enhance the photo properties of lignin even more, gives us, again, more measurements of what's going on in terms of resolution for lignin, which depends on the loading of how much lignin we add, but the material properties, in this case, stiffness goes up, which is good, strength up, tensile strength goes up, which is great, elongation goes down, so the material becomes less ductile, more rigid, all good news. So the question is, what does the future hold? We're doing a lot of investigation of resin components. Can we make resins from up to 100% renewable materials, for example, using soybean oil and lignin? But we do a lot of science, engineering, and marketing of products to make new products entirely from biomass to do 3D printing. So I'm going to stop there and give you some time for questions. If anybody has any, I'd love to answer them. Thanks so much for paying attention. I should mention that none of this work would be possible without the graduate students and postdocs and undergraduates who work in my lab. I sit in the office and live vicariously through them. They come and tell me about all their great results, and I say, good job. I wish I was there with you, but you guys know how it goes. So thank you very much. I'd be happy to answer any questions that you have.
All right, terrific. We do have time for a few questions. So if we have any in the crowd, or if you note anything coming up on the question and answer box. So anyone in the room with a question? And maybe while they're thinking, I'm curious, Dr. Chmely, you're showing some very specific molecules that you're working with, and yet it seems that biomass is highly variable in terms of, you know, when we talk about mass bio, we're talking about different species and different locations and the year-to-year variations. How much of that is an issue or a problem with what you're trying to achieve?
Yeah, it's a great question. And it can be a really big issue, even among, so we like to think about differences between, say, hardwoods and softwoods and grasses. And those are certainly very different. You know, corn is very different than poplar, is very different than pine. And even among the same species, but like different parts of the field, the chemical composition can be different based on how many nutrients this particular plant got versus this one. And so we like to talk about averages over ranges. That's where that NMR spectrum really helps us, because we move away from looking at specific models and look more at, well, what does the average composition of this particular species look like? And from that, we hope that we can get some useful information.
Other questions?
I have one question. Does that lignin resin works in other types of 3D printing strategies? Or?
This is a great question. So the lignin resin that we use, because it's a liquid, wouldn't be useful for the other popular 3D printing technology, which is called fused deposition modeling, which uses a solid. It's kind of like squirting toothpaste, where you take a solid and you soften it. I think you could probably make blends with lignin. You'd have to probably pre-polymerize your material. The other issue is that because our material is cross-linked, it becomes one that will not soften as you heat it up. And so you can't extrude it. So you got to be careful with what, so a lot of times for like FDM printing, lignin is mixed with polylactic acid, which is a renewable material. And those you can 3D print by FDM, but these specific ones probably not.
I have a question for Tom. I just had a question about, like, this is really new to me. So what would you use? I know you'd use this resin for 3D print, but what's the point? At the end of the day, like, is my question.
Yeah, that's a great question. So we think that the materials, if we're really interested in 3D printing on what I call a very large scale. So whereas 3D printers nowadays, you could buy on Amazon, $300, one of these printers, and print as many Baby Yoda keychains as you want, right? Not a particularly useful product. But if we could use materials like these that are sustainable and renewable at a large scale, we could print now things that are useful for infrastructure components. So one thing that we target is, can we 3D print wind energy rotor blades? Because wind energy rotor blades, the things that are actually turning on a wind energy rotor or on a windmill, are made of composite materials that are not recyclable. Actually grind those up and bury them in a landfill at the end of their life. But here, we may still have to grind these up and put them in a landfill, but if they all come from plant material, the question is, are they innocuous? So when we put them in the ground, they don't cause any harm. And if so, in that case, they would actually be sequestering atmospheric carbon, right? Because the plant that grows takes CO2 out of the atmosphere, and then we put it in a wind energy rotor, and it lives that carbon for 50 years. It's not back in the atmosphere anymore. Then we grind it up and put it in the ground, and it lives for hundreds of years as soil amendment, for example. So the idea is to think really big, infrastructure or construction components. Can we replace some of the plastics that are used in building materials? Those types of things. Yeah, it's a great question. We don't just print, or we don't hope to just print the dog bones for sure.
Okay.
We do have a lot of baby Yodas though.
Yeah.
And are people looking at that end of use applications yet, or is that still coming?
Yeah, not yet. We need to find the right person. I think that I'm really interested in exploring how we could use this material as a soil amendment, much in the same way that we use biochar, that it wouldn't be nutrients, but it would help make the soil more amenable to water holding or nutrient capacity or the microbiome of the soil. So it's not actually adding nutrients, it's just helping the soil characteristics.
Okay, well, I think we're out of time. So Dr. Chmely, thank you so much. Really appreciate you presenting to us today. And for everyone who's connected, we look forward to seeing you next week for the next Mass Bio Seminar. Thank you, everyone. Thanks very much.
That's all right. Hope it didn't go over.